Okay, hello. We are working on section 11.2 today. I am re-recording, so I've already written it all out. I'm re-recording so that way it's not a bunch of short videos. It's just one, and it shows up only once in Google Classroom. It'll be easier. So here we go. Today what we're going to talk about is we're going to talk about two different kinds of tests, a test for independence and a test for homogeneity. I'll explain the difference between the two tests as we cruise through the lesson. The big deal is that they're going to be a two-way table, okay? You are going to have a table of data that goes two ways, horizontally and vertically. So you need at least a 2x2 table, okay? If you have one row of data or one column of data and that's it, that's not enough. It's only one way, not two ways. With this, the first thing before we even get into the problems, right, I want you to take a look at like how you would find an expected value. So different from a goodness of fit test, which is what we had in section 11.1. We're going to talk about like to find your expected value. It's not percentages, all right? We're seeing how the rows and the columns relate to each other. So the expected value, if you were doing this by hand, which you do need to know how to do, okay, if you're doing this by hand, your expected value, what you would do, if I put like here for this cell, I put a little star, I tallied, my row totals and my column totals. So there's 24 data points total in this table. So to find this star, it would be row total 10 times column total 4 divided by the grand total 24. So the expected value for this cell would be 1.7, which we know would fail the at least 5 counts part, like expected values all need to be at least 5. But that's how you would find it. So if you were doing this by hand, you would need to do this process for all 6 of these cells. Okay, we are not going to be doing it by hand. You do need to know how to do it by hand, but typically you're going to be able to use the amazing shortcut that you're going to learn in a few minutes on the calculator, okay? But you do need to, like multiple choice, absolutely these kinds of questions have shown up on the AP test. All right, so what we're going to do is we're going to talk about how to do a test for either independence or homogeneity. We still have the same formula, okay? The values in the table are your observed. Then you would find your expected by doing this process for all of them, okay? Your degrees of freedom are different. It's going to be your rows minus 1 times your number of columns minus 1. So for this problem, you'd have 3 rows minus 1 2 rows, 1, 2, minus 1, times 3 columns, 1, 2, 3, minus 1. Okay, so you'd have 1 times 2, you'd have 2 degrees of freedom. We need to remember that, and it can be called a contingency table, which is also a two-way table. All of these tests, all chi-squared, are always right-tailed only, always and forever. Okay. The big deal, to test for homogeneity, homogeneous means all the same, right? So we're trying to test, are all the proportions the same? So in a test of homogeneity, we test the claim that different populations have the same proportion of whatever characteristic we're looking for, okay? So the proportion of kids at Seneca who attend RCBC is equal to the proportion of kids at Cherokee who attend RCBC is equal to the proportion of kids at Shawnee is equal to the proportion of kids at Lenape, for instance, okay? The proportion of 9th graders is equal to the proportion of 10th graders is equal to the proportion of 11th graders is equal to the proportion of 12th graders who ride the bus, whatever we'd be looking for. You can, when you write out your hypotheses, you can write in words, right? Your null hypothesis is always going to be for these problems. There is no difference in the blah, blah, blah. Okay, you can also write it as P1 equals P2 equals P3 because if there's no difference, that means they're equal. And then for HA, you're going to say that there is a difference in the distribution of proportions in your situation. You could write it also as at least one proportion differs. We're not trying to figure out where the difference lies. We're just saying, is there a difference or is there not a difference? Okay, not in which one, Lenape, Shawnee, Cherokee. It's just, are they all equal to each other, or is at least one different from the others? Okay. With this, you have your conditions, all right? We need to make sure that the data come from random samples or from random groups in experiment. When we're sampling without replacement, we still need to check that our population at least 10 times our sample size, right? If you have two groups, you have to check it twice. We'll go through this. And like last time, all of our expected counts have to be at least 5. Now, pause the video and write this down. This is the be-all, end-all, best shortcut we've got in a long time. All right, so copy this down. I'm going to go through and explain this to you. All right, and we'll talk about how to get through these. Okay, and then let's just kind of talk about the problem, and I'll model those steps as we go through this problem. So Penn State. Penn State has its main campus in the town of State College, and then more than 20 smaller Commonwealth campuses around the state. The Penn State Division of Student Affairs pulled separate random samples of undergrads from both campuses about their use of online social networking. A while ago, Facebook was the most popular site with more than 80% of students having an account. So do these data provide convincing evidence of a difference in the distributions of Facebook use among the students in the two campus settings? So we're trying to say, like, do main campus kids have the same proportion of several times a month or less as Commonwealth? Do main campus have the same proportions as at least once a week as Commonwealth? I tallied them just so it's done. Okay, sometimes they're not tallied for you and you have to tally them. Sometimes they're already tallied, so always check to make sure you don't tally the tally in when you're working through it. Okay, for our parameter, we don't really have a parameter to work with here, but we do have our campuses. So our null hypothesis is there is no difference in the distributions of Facebook use between Penn State's main campus and its Commonwealth campus. And your alternate is there is a difference in the distributions of Facebook use, okay, between Penn State's main campus and its Commonwealth campus. As we're checking, we need to check our assumptions. It's stated to be random samples of their undergrads. I put all expected counts are at least 5, see below. Remember, you can only write see below if you actually write them below, okay, which I have in a minute. I'm checking is my population at least 10 times my sample size for main campus and Commonwealth. Yes, absolutely, they work out. Okay, and this is a test for homogeneity, chi-squared for homogeneity. So now what we're going to do, all right, is we're going to put this into a matrix, all right? So if we go back to these steps, okay, you're going to go under the calculator, you're going to hit menu, you're going to pick number 7, matrix, you're going to pick number 1, create a matrix. I'm sorry, I'm just checking the video part. Okay, we're gonna pick number 1, matrix. We need it to be, this problem is 3 rows and 2 columns. So 3 rows, 2 columns, press OK. We're gonna type in our matrix. Okay, so we're gonna type in 55, tab to get over, 76, tab 215, tab 157, tab 640, tab 394. Now, here's the key. See how I wrote here, move the cursor to the right of the matrix, and then click Control var. So I'm going to go to the right of the matrix. Now my cursor's outside. I'm going to hit Control var, gave an arrow, then I'm going to hit the letter A. I'm always going to call my matrix A. Right, that way when I rename the next one A, it forgets the old matrix A. So I, just out of habit, always call it A. You could call them something different every time, but then you have to remember what you called them, and that's really annoying. So I just call them A, and then you press enter, and it looks like nothing happened. But now what we have is the letter A, your calculator is going to remember, is this matrix here. All right, so now what we need to do is we want to go through and we want to find all of our stuff, okay? Your calculator is actually going to run the formula for you, which is awesome. And your calculator can also give you your expected counts. last lesson, you had to do the formula by hand, right? You had to write out this whole, like all the fractions, O minus E squared over E, O plus the next one, plus the next one. For this problem, we would need to do that 6 times because there's 6 cells of data. But your calculator can actually just do it for you. So in order to do that, we're going to go under menu. We're going to pick number 6, statistics, and then we're going to come down here to number 7, stat tests. All right, and what we're going to pick is number 8, the chi-squared two-way test. Your observed matrix is the name you just called your matrix. So since I called mine A, I could just put an A here. If you, let's say when we did that control var to store it, if you had typed in the word nonsense, then here you would need to type in the word nonsense again, which is why I always just use the letter A, short, sweet, to the point. Okay, you're going to press OK. Boom. This right here, your chi-squared, is the answer to the formula. This is your test statistic. This 19.489. My degrees of freedom, if we model how to get this by hand, your degrees of freedom, again, are rows minus 1 times columns minus 1. So we had 3 rows minus 1 times 2 columns minus 1. So we're going to get 2 times 1 is where my 2 comes from. Okay. Your p-value, they give it to you as well. Right here, my p-value, be careful, it's scientific notation, but you also need to understand that this is a right-tailed test, right? Where zeros here, infinities here. This is my 19.489 from the formula answer, my test statistic that I just got back here. So this is why I did chi-squared CDF from 19.489 to infinity, degrees of freedom 2, and that's where the p-value comes from. Your expected counts, this is, I'm telling you, this is fabulous. You can only get this table, right? This is skipping this row total minus column total divided by gram total. You can only access this if you've already done this that I just showed you, this stat test, okay? And what you're going to do is you can, and I've got the directions here, you're going to click var, and then you're going to click on the one that says stat.exp matrix, okay? And you press enter, and it's here. You press enter again, and there it is. It's in the same order. These are the expected values for every single cell, okay, which is where this came from. You can't write, see below, all expected counts are at least 5 if you don't actually write down what they are. So technically, you could have like done this earlier and written this up here, but I just wrote it here when I got to the test part. From here, everything else is the same. Our p-value is less than alpha, which means reject the null hypothesis, which means then we can conclude that the distribution of Facebook use is different among the students at Penn State's main campus versus the Commonwealth campuses. So that is a test for homogeneity. We're saying, is the proportion breakdown here and here the same, here and here, here and here? Like, are they proportionally equal to each other? The next thing we have is a test for independence, okay? And a test for independence is when we're going to test that the null hypothesis that the row variable and the column variable in a two-way table or contingency table are not related, okay? You can put these either way. So here's the big difference. In a test for independence, you're going to have, and I actually put this on the back page, right? So you've got homogeneity here and you have independence here. So independence, in homogeneity, sorry, where we just worked, right? We had 2 samples. We had main campus and Commonwealth campus. And we were just looking at one variable. We were looking at Facebook use. So now here in independence, there's only one sample, but we're looking at 2 variables. So we're looking at a variable here and a variable here, and are these variables related to each other or not? Okay, so if we go through like here, right, this is and I'll get to this example in a minute. Sorry, I'm a little all over the place. This is talking about anger level, all right, in patients, and then heart disease, whether they have coronary heart disease or they don't. So we have a variable here and a variable here. Whereas last time it was like 2 samples. We only have 1 sample, people. Right? You can write your hypotheses 2 ways. You can write your hypotheses as there is no association, which means relationship, right? So there is no relationship between the variables, or there is a relationship between the variables. Remember, it has to be in the context of the problem. Otherwise it's not valid. Or you could choose to write this way. The 2 variables are independent in this population, which means independences, they're not related, which is what we just set up here. And then your alternate would be they're dependent, right? Or not independent, which if they're dependent, there is an association, they are related. So you can pick this language or this language. That's up to you. All right. Conditions, we've got data has to come from a random sample of the population. There can't be an experiment here because then you have 2 variables, and you can't have 2 variables in an experiment, right? To see if the variables are related to each other. We're going to sample without replacement, n is less than, population is at least 10 times our sample size. I made a note. There's only 1 population in these types of problems, so you only need to check it once. And again, all chapter large counts need to be at least expected. Large counts means your expected counts need to be at least 5. I have no clue why I gave you all this empty space. Maybe draw yourself a picture. So let's cruise through this. Okay. A study followed a random sample of 8,474 people with normal blood pressure for about 4 years. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale Test, which measures how prone they are to sudden anger. Researchers also recorded whether each individual developed coronary heart disease after the 4 years or during the 4 years. This includes people who had heart attacks and those who needed medical treatment for heart disease. So we're trying to see is there significant evidence to conclude that the anger level and heart disease are associated or related in people with normal blood pressure. So your null hypothesis is always there's no relationship. So I put there's no association or relationship between anger level and heart disease. You could have also said anger level and heart disease are independent of each other. Okay, I should have included for people with normal blood pressure in here. Okay, that's our population of interest. So that would really be our parameter. If you want to identify your parameter here, it would be your population of interest as people with normal blood pressure. Your alternate would be there is an association or there is a relationship or they're dependent. Anger level and heart disease are dependent. You have a random sample, okay, it's stated to be a random sample. All of our expected counts are at least 5. We'll see that in a minute. And it's reasonable to assume that there's at least 10 times 8,474 or at least 84,740 people with normal blood pressure. Okay, we have a chi-squared test of independence. And then why don't we practice again? Okay, so what we're going to do is we're going to go menu. We're going to turn it on. Mrs. McMichael. We're going to hit menu. Number 7, matrix. Number 1, create. Number 1, a matrix. Okay, this time we have 2 rows and we have 3 columns. So it looks just like we have. We're going to type in 53, tab 110, tab 27, tab 3057, tab 4621, tab 606. Okay, go to the right, do Control var, that stores it as A, press enter. This now erased the old A and gave us a new A. Now I can go menu, stats, stat tests, number 8 chi-squared 2A test, and I'm going to type in A because I just called it matrix A. All right, here is my formula answer. Here's my p-value. Here's my degrees of freedom. Okay, so here's my formula answer. Here's my p-value, my degrees of freedom. You have to include your degrees of freedom. That pairs with your p-value, okay? I get my expected values. Once I've completed this, I can hit var, and then it's right here, stat.expected matrix. Press enter. There you go. You might just need to scroll to the right. Like if you go back up, you can go to the right so you can see the rest of the numbers. And then you can just tab down to get out of it. Okay, so you need to write down your expected values because again, this isn't valid if you don't actually write them. Okay, they could be called expected counts. They could be called expected values. That doesn't matter. My p-value here is less than my alpha, which means I just meant to put that there and didn't, which means I need to reject my null hypothesis, which means there is an association, okay, or they're not independent, or that it's dependent between anger level and heart disease. Anger level and heart disease, according to this problem, are related to each other. All right, so this last page kind of goes through what to use when. All right, if you have one sample and one variable, then that's goodness of fit. Two or more samples with one variable is homogeneity. One sample with two variables is a test for independence. Okay, kind of breaks everything down for you. And I wrote it here. Okay, goodness of fit is one variable in one population. Homogeneity is one variable in two or more populations. And then a test for independence or association is when you have two variables in one population. So I hope you took marvelous notes. I hope you practiced with the calculator as I went through it so that, you know, as you practice, it gets more and more natural. And make sure you jot down what kind of questions you have so you can ask them when we meet. Good job today.